Lava Earth, the eternal glow. Close your eyes for a moment and imagine standing at the edge of forever. Not forever in time, but forever in heat, in light, in the raw, untamed energy of creation itself. Picture, if you will, a world where the very ground beneath your feet glows like the embers of a cosmic campfire, where the air shimmers with waves of heat that dance like spirits in the twilight, and where the sky burns not with the gentle warmth of our familiar sun, but with the fierce primal fire of a planet being born. This is not a world you could visit, dear listener. This is not a world where life as we know it could draw even a single breath. This is Earth 4.5 billion years ago, when our home was nothing more than a ball of molten rock spinning through the darkness of space, glowing like an ember dropped from the forge of the gods themselves. Tonight, we journey back to that time before time, to that world before worlds, to understand how our peaceful blue marble of a planet began its existence as something far more fierce and beautiful and terrible than anything we could imagine today. We journey to the Hadean Aeon, a name that speaks of Hades, of the underworld, of a realm of fire that would have seemed like the very definition of hell to any creature that might have witnessed it. But there was no one to witness it then, no eyes to see the spectacle, no hearts to feel the terror and the wonder. There was only the Earth itself, learning how to be a planet, learning the slow, patient art of cooling, of settling, of becoming the world that would one day cradle all of us. So pull your blanket a little closer tonight, feel the comfort of your solid ground beneath you, and let me tell you the story of when our world was fire, when the very rocks flowed like rivers, and when the future of all life hung in the balance of temperature and time. Before the beginning. To understand the story of Lava Earth, we must first travel even further back, to a time when there was no Earth at all. Picture, if you can, the solar system as a nursery. Not a nursery for children, but a nursery for worlds. 4.5 billion years ago, where our familiar planets now dance their eternal ballet around the sun, there was instead a vast swirling disk of dust and gas and tiny particles of rock and ice. This was the solar nebula, a cosmic cloud that stretched billions of miles across space, slowly spinning like the grandest merry-go-round ever imagined. Within this cloud, particles no bigger than grains of sand were beginning a process so gradual, so patient, that it would take millions of years to complete. They were beginning to stick together. It started small, as all great things do. One grain of dust would bump into another, and sometimes, just sometimes, they would cling to each other with the gentlest of touches. Static electricity, the same force that makes your hair stand up when you rub a balloon against it, was one of the invisible hands guiding this cosmic construction project. Gravity, still weak at such tiny scales, was another. Slowly, grain by grain, these particles began to form larger clumps. The clumps became pebbles, the pebbles became rocks. The rocks became boulders, and the boulders, drawn together by gravity's patient pull, began to form something that had never existed before in this corner of space. They began to form what we now call Earth. But this early Earth was nothing like the world we know today. There were no oceans, no continents, no atmosphere as we understand it. There was simply a growing ball of rock, constantly pelted by more and more debris from space, growing larger with each collision, and with each collision, growing hotter. You see, dear listener, every time two objects collide in space, their motion, their kinetic energy, transforms into heat. It's the same principle that makes your hands warm when you rub them together rapidly, but on a scale so vast that it defies comprehension. With each asteroid, each comet, each chunk of debris that slammed into the growing Earth, the temperature of our planet forming rose higher and higher. Scientists have calculated that during this period of heavy bombardment, a time they call the Hadean Aeon, the surface temperature of Earth may have reached as high as 2,000 degrees Celsius. To put that in perspective, that's hot enough to melt copper, hot enough to turn sand into glass, hot enough that the very rocks themselves became liquid and flowed like honey. This was the birth of lava Earth, a world where the boundary between solid and liquid had lost all meaning, where the ground itself was alive with motion, flowing and churning and glowing with the heat of its own creation. The architecture of fire. Imagine for a moment that you could somehow stand on the surface of this ancient Earth, protected by some impossible suit that could shield you from the crushing heat and toxic atmosphere. What would you see? The horizon would glow with the deep, rich red of molten rock, stretching endlessly in all directions like an ocean of fire. But unlike the steady, predictable surface of water, this ocean would be alive with motion. Great bubbles of superheated gas would rise from the depths and burst at the surface, sending sprays of liquid rock arcing through the air like the most magnificent and terrible fireworks display ever conceived. The ground beneath your feet, if we can call it ground when it flows like a river, would pulse and heave with convection currents. Hot material from deep below would rise to the surface, cool slightly in the thin atmosphere, then sink back down again, only to be replaced by more molten rock rising from the depths. It would be like watching a vast slow-motion ballet performed by the Earth itself, a dance that had been going on for millions of years and would continue for millions more. The air above this molten surface would shimmer with heat waves so intense that they would distort your vision, making the already alien landscape ripple and bend like a mirage. And what an atmosphere it was, if we can even call it that. There was no oxygen then, no nitrogen as we know it today. Instead, the early Earth's atmosphere was a toxic brew of water vapor, carbon dioxide, methane, and hydrogen sulfide, the same gas that gives rotten eggs their distinctive smell. But perhaps most remarkable of all would be the sound. We think of space as silent, and indeed it is, but the early Earth was far from silent. The constant bubbling and churning of the molten surface would create a symphony of pops and gurgles and deep, resonant rumblings that would vibrate through the ground and up through your body. The occasional impact of an asteroid or comet would add percussion to this primordial orchestra, crashes and explosions that would make thunder seem like a whisper by comparison. And through it all, the glow. Day and night, though these concepts had little meaning on a world where the ground itself provided more light than any sun, the entire planet would radiate with the warm, orange-red light of molten rock. From space, Earth would have looked like a dimly glowing coal, an ember floating in the cosmic darkness. This was not a static world, despite its appearance of endless, unchanging fire. Even in its molten state, Earth was beginning to differentiate, to sort itself into layers based on density and temperature. The heaviest elements, particularly iron and nickel, were slowly sinking toward the center, while lighter materials rose toward the surface. This process, called planetary differentiation, was laying the groundwork for the structure our planet still maintains today. A dense iron core, surrounded by a mantle of rock, topped by a thin crust. But that crust, the solid foundation that we walk on today, that was still hundreds of millions of years in the future. For now, there was only the magma ocean, a global sea of molten rock that covered the entire planet to a depth of hundreds of miles. The dance of heat and time. Time moves differently when you're watching rocks melt. Not just because the process is slow, though it is almost impossibly slow by human standards, but because you're witnessing something that exists on a scale so vast that it changes how you think about permanence, about change, about the very nature of what it means for something to exist. On the early Earth, a single convection cycle in the magma ocean, one complete circulation of molten rock rising from the depths, cooling at the surface and sinking back down again, might take thousands of years. Imagine that, a single breath of the planet lasting longer than all of recorded human history. And yet, from the perspective of planetary formation, these were quick, restless movements. The early Earth was like a newborn that couldn't settle down, constantly shifting and churning as it tried to find its equilibrium. The heat from the constant bombardment of asteroids and comets kept the surface molten, but even as new impacts added energy to the system, the planet was slowly, steadily losing heat to space. This is one of the fundamental laws of the universe. Heat always flows from hot objects to cold ones, and space, dear listener, is very, very cold. The cosmic background temperature is about minus 270 degrees Celsius, nearly absolute zero, the point at which all atomic motion ceases. Against this frigid backdrop, even our molten Earth was gradually cooling. But cooling in geological terms is a relative concept. We're not talking about the way a cup of coffee cools on your desk, losing its warmth in the matter of minutes. Planetary cooling happens on timescales that dwarf human comprehension. The Earth's magma ocean would remain molten for tens of millions of years, slowly radiating its heat into space grain by grain, degree by degree. During this long cooling period, something beautiful was happening at the boundary between the molten planet and the vacuum of space. Water vapor in the early atmosphere was beginning to condense into tiny droplets, then into larger droplets, then into actual drops of liquid water. But these drops never had a chance to reach the surface. The moment they formed in the upper atmosphere, they would begin to fall through the layers of hot, toxic gas below, and as they fell, they would heat up and evaporate again, rising back into the sky as vapor. This created a kind of eternal rain cycle, water constantly condensing and falling and evaporating and rising again over and over for millions upon millions of years. It was as if the planet was learning how to have weather, practicing the gentle art of precipitation in an environment where it could never quite succeed. And slowly, oh so slowly, the surface began to cool. Not uniformly, the planet was far too chaotic for that, but in patches and spots. Temporary islands of relative coolness where the first hints of solid crust could begin to form. These early patches of crust were incredibly thin and fragile, like the skin that forms on the top of cooling pudding. They would form, float on the surface of the magma ocean for a while, then be broken apart and dissolved back into the molten rock by convection currents or new impacts from space. It was a constant cycle of creation and destruction, the planet trying again and again to grow a solid skin. The birth of zircon, witnesses to creation. In this world of endless fire and flux, something remarkable happened. Something so small and seemingly insignificant that you might overlook it entirely, but so important that it would change our understanding of Earth's early history forever. Deep within the cooling margins of the magma ocean, where temperatures had dropped just enough to allow solid minerals to form, tiny crystals began to grow. These crystals were made of zircon, zirconium silicate, a mineral that forms under very specific conditions of temperature and chemistry. Each crystal was smaller than a grain of sand, invisible to the naked eye, but they possessed two properties that would make them invaluable to scientists billions of years later. First, zircon crystals are nearly indestructible. They can survive temperatures that would melt most other minerals. They resist chemical weathering that would dissolve limestone or even granite. They are, in essence, tiny time capsules made of the most durable natural material on Earth. Second, when zircon crystals form, they trap tiny amounts of radioactive uranium within their crystal structure. This uranium decays at a perfectly predictable rate, transforming into lead over millions and billions of years. By measuring the ratio of uranium to lead in ancient zircon crystals, scientists can determine exactly when those crystals formed, giving us a window into the earliest days of our planet. The oldest zircon crystals ever found on Earth are 4.4 billion years old, formed when the planet was only about 150 million years old. These ancient crystals tell us something amazing about those early days. Even in the midst of the global magma ocean, there were pockets of relatively cool water where solid minerals could form and survive. Think about that for a moment. These tiny crystals are the oldest pieces of Earth that still exist today. They formed when the planet was a ball of molten rock, survived the entire history of our world, the formation of the first oceans, the emergence of life on the dry land, the rise and fall of countless mountain ranges, the evolution of complex organisms, the age of dinosaurs, the birth of mammals, the evolution of humans, and all of recorded history, and they're still here, still carrying within their crystal structure the chemical signature of Earth's fiery birth. When you hold a zircon crystal in your hand, and they're not uncommon, you can find them on many beaches around the world, you are literally holding a piece of the earliest Earth, a fragment that was there at the very beginning, a witness to the creation of our world. The Great Cooling. Music becomes more spacious and contemplative, with longer notes suggesting the passage of vast time. But all fires, no matter how fierce, must eventually burn themselves out. The early Earth, for all its molten fury, was no exception to this fundamental law of the universe. As the heavy bombardment of asteroids and comets began to wane, as the planet grew large enough that new impacts became less frequent, the balance between heat gained and heat lost began to shift. The cooling happened so gradually that if you could somehow observe it from day to day, or even from century to century, you might not notice any change at all. But over millions of years, the difference became dramatic. The deep red glow of the planet's surface began to fade from cherry red to a duller, darker crimson. The constant bubbling and churning of the magma ocean began to slow, like a pot of soup cooling on the stove. And then, in some places, probably in the polar regions where heat loss to space was most efficient, or in areas where particularly large impacts had thrown up massive amounts of debris that shielded the surface from the sun, something unprecedented happened. The surface of the magma ocean began to develop a skin. This first crust was incredibly thin, perhaps only a few miles thick, floating on an ocean of molten rock that extended hundreds of miles down into the planet's interior. It was unstable, constantly cracking and reforming in new patterns, but it was solid. For the first time in Earth's history, there was a boundary between the molten interior and the toxic atmosphere above. Imagine that first moment when a patch of Earth's surface solidified completely. After hundreds of millions of years of constant motion, constant flow, constant change, suddenly there was a piece of ground that would hold still. It was a turning point as significant as the first time a human stood upright, or the first time life emerged from the ocean onto dry land. But this early crust was not like the stable continents we know today. It was more like sea ice in the Arctic, constantly forming, breaking apart, and reforming in new patterns. Convection currents in the molten rock below would crack the crust from underneath, allowing magma to well up and create new sections of solid rock. The crust would thicken slowly, like ice forming on a pond in winter, but it was still fragile, still temporary. During this period, Earth would have been a patchwork world, some areas covered with thin, dark crust, others still showing the bright glow of molten rock beneath. From space, the planet might have looked like a puzzle with missing pieces, or like a coal fire that was slowly dying, with some embers still glowing bright while others had cooled to ash. The atmosphere during this time was still hostile to any form of life as we know it, but it was beginning to change as well. As the surface cooled, some of the water vapor that had been locked in the atmosphere for millions of years began to condense more successfully. The eternal rain that had never quite reached the ground was finally beginning to fall as actual drops of liquid water. But of course, when these first raindrops hit the still hot surface, they would have instantly flashed into steam rising back into the atmosphere in great clouds of vapor. But gradually, as more and more of the surface solidified and cooled below the boiling point of water, some of those raindrops began to survive their journey to the ground. The first rains. Picture, if you will, the first rainstorm in the history of the world. Not a gentle spring shower or a summer thunderstorm, but something far more dramatic, a deluge that had been building in the atmosphere for millions of years, finally finding a surface cool enough to welcome it. The early Earth's atmosphere was thick with water vapor, far more than our modern atmosphere contains. For millions of years, this water had been trapped in an endless cycle of evaporation and condensation, never able to complete its journey to the ground because the surface was simply too hot. But now, with patches of solid crust providing areas of relative coolness, the stage was set for the first precipitation in planetary history. When the rains finally came, they came with a fury that would have dwarfed any storm in recorded history. Imagine clouds so thick that they blocked out the sun entirely, though at this point the glow from the planet's surface provided more light than the sun anyway. Imagine raindrops the size of marbles falling from great heights through the thick, toxic atmosphere. But these were not gentle rains. The early atmosphere was rich in carbon dioxide, sulfur compounds, and other chemicals that would make the rainwater highly acidic, more like battery acid than the relatively pure water that falls today. When this acid rain hit the newly formed rock crust, it began a process of chemical weathering that would help shape the early Earth's surface. The acid in the rainwater would react with minerals in the rock, dissolving some components and leaving others behind. This chemical weathering was one of the first steps in creating soil, though it would be billions of years before anything would grow in it. It was also the beginning of the long process by which the atmosphere would gradually lose its toxic gases and become more hospitable to life. But perhaps most importantly, as more and more of the surface cooled below the boiling point of water, some of that rain began to accumulate. In low-lying areas where the crust had cracked or sagged, pools of hot, acidic water began to form. These were not the clear, blue oceans we know today. They were more like the hot springs in places like Yellowstone, bubbling with dissolved minerals and heated by the still molten rock below. These first bodies of standing water were small and temporary. Steam would rise from their surfaces, and they would often boil away entirely when nearby volcanic activity raised the local temperature. But they were a beginning. The first time in Earth's history that liquid water had been able to exist stably on the surface. Gradually, as the cooling continued and more of the surface stabilized, these pools grew larger and more permanent. They began to connect with each other, forming the first rivers and streams. The water cycle, that fundamental process that drives weather and climate on our planet, was finally beginning to function. The birth of the ocean. The transition from isolated pools of hot water to the first true ocean was not a sudden event, rather a gradual process that took millions of years. As the Earth continued to cool and more of its surface solidified, water continued to fall from the atmosphere and accumulate in the lowest places. But where did all this water come from originally? This question puzzled scientists for many years, and the answer turns out to be more complex and beautiful than anyone initially imagined. Some of the water was present in the original materials that formed Earth, locked up in hydrated minerals and released as the planet heated up during its formation. But much of it came from space, delivered by countless comets and asteroids that bombarded the early Earth. Comets, those beautiful wanderers that occasionally grace our night sky with their glowing tails, are essentially dirty snowballs, chunks of ice and rock left over from the formation of the solar system. During the period of heavy bombardment, millions of these icy visitors crashed into Earth, each one adding its store of frozen water to our planet's growing supply. It's a poetic thought, isn't it, that the water in the oceans, the water that would eventually nurture the first life and sustain all life that followed, came to us from the deep cold of space, carried by celestial messengers over billions of miles and millions of years. As this water accumulated, it began to fill the lowest areas of the newly formed crust. These early ocean basins were not like the smooth, deep basins we know today. The crust was still thin and unstable, constantly cracking and reforming. Volcanic activity was widespread, with underwater volcanoes constantly adding new material to the ocean floor and heating the water from below. The first ocean, therefore, was very different from the oceans of today. It was hot, probably close to the boiling point in many places. It was shallow compared to modern oceans because the crust hadn't yet had time to develop the deep basins that characterize our current ocean floors. And it was incredibly rich in dissolved minerals, leached from the volcanic rocks by the hot, acidic water. This mineral-rich water was the color of rust in many places, stained by iron compounds dissolved from the rocks. In other areas, it might have been green with dissolved copper minerals or yellow with sulfur compounds. It was less like the clear blue water we associate with the ocean today and more like the hot springs you might find in volcanic regions. Steam would constantly rise from the surface of this early ocean, creating a perpetual haze that would have made the boundary between water and air indistinct. The atmospheric pressure was higher then, and the thick atmosphere trapped heat efficiently, creating a greenhouse effect that kept the surface temperature well above what it would be today at the same distance from the sun. But despite its alien appearance, this early ocean represented a crucial milestone in Earth's development. For the first time since the planet's formation, there was a stable environment where complex chemical reactions could take place. The hot, mineral-rich water provided a natural laboratory where the chemical building blocks of life could begin to form and interact. The chemistry of possibility. In the depths of that first ocean, something remarkable was happening. The hot, mineral-rich water was not just a passive container for dissolved rock and gas. It was becoming an active chemical laboratory where the ingredients for life were beginning to stir. The early ocean was what chemists call a reducing environment, meaning it was rich in hydrogen and poor in oxygen. This might seem hostile to life as we know it, since we depend on oxygen to breathe, but it was actually the perfect environment for the complex organic chemistry that would eventually lead to living things. In this reducing environment, carbon dioxide from the atmosphere could react with hydrogen and minerals from the rocks to form simple organic molecules, the carbon-based compounds that form the foundation of all life. Methane, formaldehyde, amino acids, and even more complex organic compounds began to accumulate in the ocean water. Scientists have recreated similar conditions in laboratory experiments, and they consistently find that these basic organic molecules form spontaneously when the right ingredients are present. It's as if the universe has a natural tendency toward complexity, toward the formation of the building blocks of life, given the right conditions. But the early ocean was not uniform in its chemistry. Different areas had different temperatures, different mineral compositions, different levels of acidity. This created a vast array of microenvironments, each potentially suitable for different types of chemical reactions. Some areas might have been rich in iron and sulfur, others in carbon and phosphorus. Some might have been nearly boiling, others merely hot. Perhaps most importantly, the interface between the hot water and the volcanic rocks on the ocean floor created conditions that were particularly favorable for complex chemistry. When hot, mineral-rich water comes in contact with certain types of rock, it can catalyze chemical reactions, speed them up, and make them more likely to occur. Modern scientists have found that certain minerals, particularly those containing iron and sulfur that would have been common on the early Earth, can act as primitive catalysts, helping to form complex organic molecules from simpler ingredients. Some researchers believe that these mineral catalysts may have been crucial to the origin of life, serving as the first metabolism, the first organized system of chemical reactions that could sustain itself and grow. The early ocean was also subject to constant energy inputs that could drive chemical reactions. Lightning was probably much more common in the thick, electrically active atmosphere. Volcanic activity provided both heat and new chemical ingredients, and most importantly, the sun provided a constant stream of ultraviolet radiation that could break apart simple molecules and allow them to recombine in new ways. Without the protective ozone layer that shields us today, the early Earth's surface was bathed in high-energy ultraviolet light. This radiation, which would be deadly to modern life, may have been essential to the formation of the first complex organic molecules. UV light can provide the energy needed to forge chemical bonds that would not form under gentler conditions. The pulse of a young planet. During this period of Earth's history, still deep in the Hadean eon, the planet had developed something resembling a pulse, a rhythm of geologic activity that would continue, in various forms, for the rest of Earth's history. This pulse was driven by the flow of heat from the planet's interior to its surface, and it manifested in cycles of volcanic activity, crustal formation, and destruction. The Earth's interior was much hotter then than it is today. The radioactive decay of uranium, thorium, and potassium, elements that had been incorporated into the planet during its formation, was generating enormous amounts of heat. Additionally, the planet was still contracting slightly as it cooled, and this gravitational compression also generated heat. All of this internal heat had to go somewhere, and the primary way it escaped was through volcanic activity. But the volcanism of the early Earth was unlike anything we see today. Without thick, stable continents to constrain it, volcanic activity could occur almost anywhere on the planet's surface. Great rifts would open in the thin crust, allowing molten rock to pour out directly from the interior. These early volcanic eruptions were not the dramatic, explosive events we might imagine. Because the crust was so thin
and the pressure differences were relatively small, most volcanism took the form of gentle effusive eruptions. Molten rock simply welling up from below and spreading across the surface like spilled honey. But the scale was enormous. Single volcanic events might cover areas the size of modern countries. The volcanic plains that formed during this period were hundreds of times larger than anything produced by volcanoes today. And because the crust was still unstable, these volcanic plains would often crack and subside, only to be covered by new eruptions, in an endless cycle of creation and destruction. This constant volcanic activity had a profound effect on the early atmosphere and ocean. Each eruption would release gases that had been dissolved in the molten rock: water vapor, carbon dioxide, sulfur compounds, and many others. These gases would modify the composition of the atmosphere, sometimes dramatically. Sulfur compounds from volcanic eruptions could react with water in the atmosphere to form sulfuric acid, making the rain even more acidic than it already was. Carbon dioxide would thicken the atmosphere and strengthen the greenhouse effect, helping to keep the surface warm despite the gradually cooling interior.
But perhaps most importantly, volcanic activity was constantly adding new material to the ocean. Each underwater eruption would spill molten rock directly into the seawater, where it would cool rapidly and form new sections of ocean floor. This process was constantly renewing the interface between rock and water, where complex chemistry could occur. The early ocean floor was therefore very different from the deep, stable ocean basins we know today. It was young, hot, and chemically active. Fresh volcanic rock, still warm from its formation, provided an ideal surface for chemical reactions. Hydrothermal vents, underwater hot springs, where superheated water rich in dissolved minerals would erupt from the seafloor, were probably much more common than they are today. These hydrothermal vents created local areas of extreme temperature and chemical gradients. Water near the vents might be hot enough to sterilize any modern organism, while water just a few meters away might be merely warm. This created a complex three-dimensional environment where different types of chemistry could occur in close proximity. The Great Differentiation. Music becomes more structured and layered, suggesting the organization of complex systems. As the Earth continued to evolve during these early hundreds of millions of years, a process of fundamental importance was taking place deep within the planet. The Great Differentiation, the separation of the Earth's materials by density, was creating the layered structure that still characterizes our planet today. When Earth first formed from the collision of countless planetesimals, it was a fairly homogeneous mixture of rock, metal, and ice. But as the planet heated up and much of its material became molten, gravity began to sort these materials by density. The heaviest materials, primarily iron and nickel, began to sink toward the center, while lighter materials rose toward the surface. This process of differentiation was not gentle or gradual. As massive amounts of molten iron sank through the liquid rock mantle toward the planet's center, they released enormous amounts of gravitational potential energy. This energy was converted to heat, causing temperatures throughout the planet to rise even higher than they had been during the initial bombardment period. Some scientists believe that this iron catastrophe, the period when most of the planet's iron sank to form the core, may have been so energetically violent that it temporarily remelted the entire planet. If true, this means that the early formation of a solid crust was interrupted by a period when the entire Earth became molten again, a global magma ocean that was even more complete than the initial one. But eventually, as the iron settled into the core and the energy of differentiation was radiated away into space, the planet began to organize itself into the structure we know today. The dense iron-nickel core formed at the center, surrounded by a thick mantle of hot rock, topped by a thin crust of lighter materials.
This differentiation had profound consequences for Earth's future evolution. The formation of a metallic core created the conditions necessary for Earth to generate a magnetic field, something that would prove crucial for protecting the planet's atmosphere and any future life from harmful solar radiation. The differentiation also changed the chemistry of the planet's surface. As heavy metals sank toward the core, the crust became enriched in lighter elements like silicon, aluminum, and the alkali metals. These elements would form the basis of the continental rocks that would eventually rise above sea level and create the first dry land. But perhaps most importantly for the story we're telling tonight, differentiation changed the nature of volcanic activity on Earth. Instead of the relatively homogeneous magma that characterized the earliest volcanic eruptions, the mantle now had a more complex composition. Different types of volcanic activity could produce rocks with different chemical compositions, creating more diverse environments for chemical evolution. The differentiated Earth also developed more efficient mechanisms for heat transport. Convection currents in the now liquid outer core began to generate the planet's magnetic field, while convection in the mantle created the slow but powerful movements that would eventually drive plate tectonics. During this period, the Earth was beginning to develop the fundamental characteristics that would define it for the rest of its history. It was no longer just a ball of molten rock slowly cooling in space. It was becoming a complex, dynamic system with a hot interior, a thin solid crust, a growing ocean, and a thick atmosphere. Cycles within cycles. Music develops multiple interwoven rhythmic patterns, suggesting the complexity of interconnected systems. By now, perhaps 200 or 300 million years after its formation, Earth had developed a complex web of interconnected cycles that would regulate its behavior for billions of years to come. These were not the familiar cycles we know today, the water cycle, the carbon cycle, the seasons, but their primitive ancestors, the first tentative experiments in planetary self-regulation. The most fundamental of these cycles was the heat cycle. Heat generated in the interior of the Earth by radioactive decay and gravitational compression would rise through the mantle by convection, reach the surface through volcanic activity, and then radiate away into space. This cycle regulated the Earth's internal temperature and drove most of its geological activity.
But this heat cycle was coupled to other cycles in complex ways. Volcanic activity would release gases into the atmosphere, thickening it and enhancing the greenhouse effect, which would slow the rate of heat loss to space. But volcanic activity would also release water vapor, which could condense and fall as rain, cooling the surface and thinning the atmosphere through chemical reactions with the rocks. The early water cycle was particularly complex. Water would evaporate from the hot ocean surface, rise high into the atmosphere, condense into clouds, fall as acid rain, react with volcanic rocks, dissolve minerals, flow back to the ocean as mineral-rich rivers, and begin the cycle again. But each time around this cycle, the chemistry of both the atmosphere and the ocean would change slightly. The acid rain was gradually neutralizing itself by reacting with basic minerals in the rocks. Each time rainwater dissolved limestone or other alkaline rocks, it would become less acidic. Over millions of years, this process was slowly making the rain, and therefore the ocean, less hostile to the complex chemistry that might eventually lead to life. At the same time, the constant weathering of rocks was adding more and more dissolved minerals to the ocean. Some of these minerals would precipitate out of solution when the water became saturated, forming the first sedimentary rocks. Others would remain dissolved, creating increasingly complex chemical environments where new types of reactions could occur. The carbon cycle was also beginning to establish itself during this period. Carbon dioxide from volcanic eruptions would dissolve in the ocean water, making it more acidic. This acidic water would then react more readily with carbonate minerals in the rocks, releasing more carbon dioxide in some cases, or precipitating it as solid carbonates in others. The balance between these processes would help regulate the amount of carbon dioxide in the atmosphere, and therefore the strength of the greenhouse effect. But perhaps most fascinating was the emergence of what we might call feedback loops, situations where the result of a process would influence the process. For example, if volcanic activity increased, it would release more carbon dioxide into the atmosphere, strengthening the greenhouse effect and raising global temperatures. Higher temperatures would increase the rate of chemical weathering, which would neutralize more atmospheric carbon dioxide, eventually reducing the greenhouse effect and cooling the planet. These feedback mechanisms gave the Earth a primitive form of self-regulation, a tendency to return to equilibrium when disturbed. It was as if the planet was learning how to maintain a stable environment, developing the skills it would need to keep conditions suitable for life once life appeared. During this period, the Earth was also beginning to develop regional differences in climate and geology. The planet was rotating fast then. A day was only about 6 hours long, and this rapid rotation, combined with the thick atmosphere, created powerful wind patterns that could transport heat and moisture around the globe. But the rapid rotation also created strong Coriolis effects, breaking up these global circulation patterns into smaller, more localized weather systems. Different parts of the planet began to experience different conditions. Some areas might be perpetually cloudy and cool, others clear and hot. These regional differences would create diverse environments where different types of chemical evolution could occur. The patience of stones. Music becomes more meditative, with long, sustained notes suggesting the passage of vast time. There is something profoundly humbling about contemplating the timescales involved in these early Earth processes. We humans, with our brief lifespans and our impatient natures, struggle to comprehend the extraordinary patience of geological time. But the Earth was in no hurry during those early hundreds of millions of years. It had all the time in the world, literally, to experiment, to try different configurations, to gradually find its way towards stability. Consider the formation of the first stable continents. This was not an event that happened overnight or even over millions of nights. It was a process so gradual that if you could somehow watch it happen, it would be like watching grass grow, except slower, much, much slower. The process began with a thickening of the crust in certain areas. As volcanic activity continued to add new material to the surface, some regions began to develop thicker layers of solid rock. These thicker areas were more buoyant than the thinner oceanic crust, so they began to rise slightly above the surrounding terrain. But rise is perhaps too dynamic a word for what was happening. These proto-continents rose at rates measured in millimeters per 1,000 years. Mountains grew at speeds that would make glaciers seem lightning fast by comparison. But given enough time, and the Earth had plenty of time, even these infinitesimal changes could produce dramatic results. As these thicker crustal regions rose higher, they began to experience different environmental conditions than the ocean floor. They were exposed to more direct weathering by the atmosphere. They were subject to greater temperature variations between the hot surface and the cooling depths. And eventually, the highest points began to approach the surface of the ocean. The emergence of the first dry land was one of the most significant events in Earth's history, though it happened so slowly that there was no single moment when you could say, now there is land where there was none before. It was more like the gradual exposure of a reef at low tide, except that this low tide lasted for millions of years. The first patches of exposed land were probably small and temporary, volcanic islands that would rise above the ocean surface during periods of low water levels, only to be submerged again when the water rose. But gradually, as the crust thickened and the surface cooled, more permanent land masses began to appear. These early continents were very different from the large, stable land masses we know today. They were smaller, lower, and much more geologically active. Volcanic activity was still widespread, constantly adding new material and reshaping the landscape. The boundaries between land and sea were constantly shifting as crustal movements raised or lowered different regions. But even these primitive continents represented a revolutionary change in Earth's surface environment. For the first time, there were places where rocks could be exposed directly to the atmosphere, where chemical weathering could proceed without being modulated by the ocean's chemistry. This created entirely new types of environments and entirely new possibilities for chemical evolution. The weathering of exposed continental rocks proceeded much faster than the weathering of rocks on the ocean floor. Without the moderating effect of being submerged in water, continental rocks were subject to greater temperature variations, more direct exposure to acidic rainwater, and the physical effects of thermal expansion and contraction. This enhanced weathering had profound effects on the ocean's chemistry. Rivers carrying dissolved minerals from the continents began to change the composition of seawater, adding new ingredients to the chemical mix where complex organic molecules were forming. The symphony of elements. Music becomes more complex and harmonious, with different instrumental voices representing different chemical elements. As the Earth continued its slow transformation from a world of fire to something more familiar, the chemistry of the planet's surface was becoming increasingly sophisticated. What had started as a relatively simple mixture of molten rock, vapor water, and basic atmospheric gases was evolving into a complex symphony of chemical interactions. Each element in the periodic table has its own character, its own preferences for which other elements it likes to bond with and under what conditions. In the early Earth's diverse environments, these chemical personalities were beginning to express themselves in increasingly complex ways. Iron, one of the most abundant elements in the planet's crust, was particularly important during this period. In the hot, oxygen-poor conditions that prevailed, iron existed primarily in its reduced form. Chemically speaking, this means it was eager to share electrons with other elements. This made iron incredibly reactive and important in many of the chemical processes that were occurring. Iron could bond with sulfur to form pyrite and other sulfide minerals. It could bond with oxygen, when small amounts were available, to form various oxides. It could even participate in the formation of complex organic molecules, serving as a catalyst to speed up reactions that would otherwise proceed very slowly. Sulfur, another abundant element, was equally important. Volcanic activity was constantly adding sulfur compounds to the atmosphere and ocean, where they could participate in a wide variety of chemical reactions. Hydrogen sulfide, the same compound that gives rotten eggs their smell, was probably much more common in the early atmosphere than it is today. But sulfur's importance went beyond its abundance. Sulfur-containing molecules have some unique chemical properties that make them particularly useful for building complex organic compounds. Many of the key molecules involved in modern biochemistry, including some amino acids and vitamins, contain sulfur atoms that are crucial to their function. Carbon, of course, was the star of the show when it came to complex chemistry. Carbon's ability to form long chains and complex three-dimensional structures makes it the ideal foundation for the large, complex molecules that life requires. In the early Earth's reducing atmosphere, carbon could form bonds with hydrogen to create methane, with nitrogen to create hydrogen cyanide, and with many other elements to create increasingly sophisticated organic compounds.
But carbon chemistry on the early Earth was not limited to simple gas phase reactions. The mineral surfaces on the ocean floor and the emerging continents provided ideal environments for more complex carbon chemistry. Certain minerals could serve as templates, helping to organize carbon-containing molecules into more complex arrangements. Phosphorus, though less abundant than the other elements we've discussed, was equally crucial. Phosphorus-containing compounds are essential for energy storage and transfer in all known forms of life. The early Earth's volcanic activity was gradually releasing phosphorus from the planet's interior, making it available for incorporation into increasingly complex molecules. During this period, the ocean was beginning to develop distinct chemical layers. The surface waters, in direct contact with the atmosphere, had one set of chemical conditions. The deeper waters, influenced more by reactions with the hot volcanic rocks of the ocean floor, had different conditions, and in the intermediate depths where these different water masses mixed, entirely new types of chemistry could occur. These chemical gradients created natural laboratories where different types of molecular evolution could proceed simultaneously. In some environments, simple organic molecules could form from basic ingredients. In others, these simple molecules could combine to form more complex structures. And in still others, complex molecules could be broken down and their components recycled into new forms. The early Earth was becoming a planet-sized chemistry set, with countless different experiments proceeding simultaneously in countless different environments. Most of these experiments would lead nowhere, the molecular equivalent of evolutionary dead ends, but some would stumble upon combinations that were more stable, more complex, and more interesting than anything that had existed before. The memory of water. Music becomes more flowing and liquid, with overlapping melodies suggesting the movement and memory of water. Water, that most familiar and essential of substances, was beginning to take on a central role in Earth's chemical evolution during this period. But the water of the early Earth was very different than the pure H2O that we know today. It was a complex solution, carrying the dissolved remnants of countless chemical reactions, the memory of every rock it had touched, every volcanic gas it had absorbed, every mineral it had weathered. Modern scientists sometimes speak of water as the universal solvent, a substance capable of dissolving more different materials than any other liquid. On the early Earth, this property was being tested to its limits. The hot, acidic water of the early ocean could dissolve minerals that would remain stable in today's cooler, more neutral seawater. This meant that the early ocean was incredibly rich in dissolved substances. Modern seawater contains about 3.5% dissolved salts, mostly sodium chloride, the same substance we use to season our food, but the early ocean may have contained twice that concentration or even more of dissolved materials. And unlike modern seawater, which is dominated by just a few major components, the early ocean contained significant amounts of dozens of different dissolved substances. This chemical richness had profound implications for the development of complex chemistry. In a pure water environment, chemical reactions are limited by the availability of reactants. But in the mineral-rich water of the early ocean, many different types of reactions could proceed simultaneously, limited not by the availability of basic ingredients, but by more subtle factors like temperature, acidity, and the presence of catalytic minerals. Water's unique properties as a solvent were also creating new possibilities for molecular organization. In pure water, organic molecules tend to cluster together in ways that minimize their contact with the surrounding water molecules. But in the presence of dissolved salts and other substances, these organizational patterns become more complex. Some organic molecules would be more soluble in the salt-rich early seawater, while others would be less soluble. This created natural mechanisms for concentrating certain types of molecules in certain environments. Molecules that were repelled by the salty water might concentrate at interfaces between water and air or between water and mineral surfaces, where they could interact with each other more readily. The early ocean was also beginning to develop circulation patterns that would transport dissolved substances around the globe. The combination of heating from below, due to volcanic activity on the ocean floor, and cooling from above, due to heat loss to space, created convection currents that could carry dissolved materials from one part of the ocean to another. These circulation patterns were crucial for mixing the products of chemical reactions that were occurring in different environments. A complex organic molecule that formed near a hydrothermal vent on the ocean floor might be carried by deep water currents to a completely different part of the ocean, where it would encounter different chemical conditions and different opportunities for further reactions. But water was not just a passive medium for chemical reactions, it was an active participant. Water molecules themselves could participate in chemical reactions, donating or accepting hydrogen atoms, breaking apart under the influence of high-energy radiation, or combining with other molecules to form more complex compounds. The interaction between water and the emerging continental rocks was particularly important during this period. As the first land masses began to rise above sea level, they created new opportunities for water to interact with rocks under different conditions. Rain falling on exposed continental surfaces could dissolve different minerals than seawater reacting with ocean floor rocks. This continental weathering was beginning to change the chemistry of the ocean in subtle but important ways. Different minerals dissolving in different proportions, different rates of chemical reaction under different temperature and pressure conditions. All of these factors were slowly but steadily modifying the chemical environment where the precursors to life were forming.
The architecture of emergence. During the later stages of the Hadean Eon, roughly 4 billion years ago, Earth was beginning to develop something that we might recognize as environmental stability. This doesn't mean that the planet had become calm or predictable. It was still a world of volcanic violence and chemical extremes. But it was developing persistent patterns, recurring structures, and reliable relationships between different parts of its complex system. The most important of these emerging patterns was the development of stable chemical gradients. A chemical gradient exists whenever there is a steady difference in chemical conditions between two different places. For example, between a region with high concentrations of dissolved minerals and a region with low concentrations. In the early Earth's oceans, such gradients were becoming increasingly common and increasingly stable. Hydrothermal vents created local areas of extremely high temperature and mineral concentration, surrounded by regions of cooler, less mineral-rich water. The interfaces between these different regions became zones of intense chemical activity, where the contrasting conditions could drive complex reactions. But the most significant gradients were developing at the interfaces between different phases of matter, between water and air, between water and rock, and between different types of water with different chemical compositions. These interfaces were becoming the most chemically active places on the planet. At the water-air interface, molecules could experience conditions that were neither fully aquatic nor fully atmospheric. The surface tension of water created a unique environment where certain types of molecules could accumulate and organize themselves in ways that would not be possible in either pure water or pure air. At the water-rock interface, particularly around hydrothermal vents, the contrast between the mineral-rich hot water and the solid rock surfaces created opportunities for catalytic chemistry. Certain minerals could speed up chemical reactions, lowering the energy barriers that prevented simple molecules from combining into more complex forms. Perhaps most importantly, the planet was developing what systems theorists call nested hierarchies, structures at one level of organization that provided the foundation for structures at higher levels of organization. Simple chemical reactions were creating the building blocks for more complex reactions. More complex reactions were creating the conditions for even more sophisticated chemical systems. The early Earth was also beginning to develop more sophisticated mechanisms for concentrating and organizing molecules. Evaporation at the edges of shallow pools could concentrate dissolved substances. Freezing and thawing cycles could separate different types of molecules based on their solubility. Adsorption onto mineral surfaces could organize molecules into regular patterns. These concentration and organization mechanisms were crucial because life requires not just the right molecules, but the right molecules in the right places in the right concentrations. Random chemistry might produce amino acids, but life requires amino acids organized into specific sequences to form functional proteins. The early Earth was developing the tools needed to make this transition from random chemistry to organized chemistry. The whispers of change. Music becomes more subtle and nuanced, with quiet melodies suggesting the first stirrings of something new. As we approach the end of the Hadean Eon, roughly 3.8 billion years ago, the Earth had transformed itself from a ball of molten rock into something much more subtle and complex. The changes during this final phase of the planet's earliest era were less dramatic than the spectacular volcanic activity of earlier periods, but in many ways they were more profound. The surface temperature had dropped below the boiling point of water almost everywhere except in the immediate vicinity of active volcanoes. This meant that liquid water could exist stably across most of the planet's surface, creating a truly global ocean for the first time in Earth's history. This ocean was still hot by modern standards, probably averaging 60 to 70 degrees Celsius, about the temperature of a hot bath, but it was cool enough for complex chemistry to proceed in a controlled fashion. The atmosphere was also beginning to stabilize into something resembling a steady state. The composition was still very different from today's atmosphere. There was virtually no free oxygen, and carbon dioxide levels were probably 10 to 100 times higher than they are today. But the wild swings in atmospheric composition that had characterized the earlier Hadean Aeon were becoming less common. This atmospheric stability was crucial for the development of complex chemistry, because many important chemical reactions require specific changes in gas composition and pressure. A chemical pathway that worked under one set of atmospheric conditions might be completely disrupted if those conditions changed too rapidly or too dramatically.
The planet's internal heat engine was also settling into a more regular pattern. The initial heat from planetary formation was largely dissipated, and the heat budget was now dominated by radioactive decay in the interior. This created a more predictable pattern of volcanic activity, still much more intense than today, but no longer subject to the catastrophic heat releases that had characterized the planet's earliest years. Perhaps most importantly, the chemical systems in the ocean were beginning to show the first signs of what we might call self-organization, the spontaneous formation of ordered structures from initially random conditions. In certain environments, particularly around hydrothermal vents and in shallow pools that underwent regular cycles of heating and cooling, simple organic molecules were beginning to organize themselves into more complex structures. These organized structures were still very simple compared to living cells, but they represented a crucial step toward life. Instead of just random assemblages of molecules, the Earth was beginning to produce molecular systems with recognizable patterns and behaviors. Some of these organized systems could catalyze their own formation. That is, they could speed up the chemical reactions that produced more molecules like themselves. This created positive feedback loops that could lead to the rapid accumulation of certain types of complex molecules in certain environments. Other organized systems showed primitive forms of inheritance, the ability to pass their structural patterns on to new molecular systems. This meant that successful molecular arrangements could persist and multiply, while unsuccessful arrangements would disappear. The combination of self-catalysis and inheritance created the possibility of chemical evolution, changes in molecular populations over time, driven by differential success in surviving and reproducing. This was still far from biological evolution, but it was the first step toward the kind of organized heritable complexity that defines living things. During this period, the Earth was also developing what we might think of as chemical memory, the ability of environmental conditions to influence the types of molecules that formed, which in turn influenced future environmental conditions. Successful molecular systems could modify their local environment in ways that made it more suitable for their continued existence. These developments were laying the groundwork for one of the most important transitions in Earth's history, the transition from a world of complex chemistry to a world that included living things.
The stage was being set for the emergence of life, though that emergence was still perhaps 200 million years in the future. Reflections on deep time. Music becomes contemplative and philosophical, with harmonies that suggest both vastness and intimacy. As we near the end of our journey through the Hadean Eon, it's worth pausing to reflect on what we've witnessed, not just the physical and chemical transformations of our planet, but the almost incomprehensible timescales over which these transformations occurred. The period we've been exploring, from Earth's formation 4.5 billion years ago to the end of the Hadean Eon 3.8 billion years ago, lasted approximately 700 million years. To put that span of time in perspective, consider that the entire history of complex life on Earth, from the first multicellular organisms to the present day, spans only about 600 million years. The formation period of our planet lasted longer than the entire subsequent history of complex life. Yet, during this vast span of time, no human eye witnessed the spectacular scenes we've been imagining together. No consciousness observed the first rains falling on cooling lava, the first solid ground forming on an ocean of molten rock, the first complex molecules organizing themselves in tide pools heated by the planet's internal fire. These events happened in what we might call deep solitude, transformations of cosmic significance occurring in perfect silence with no witness save the universe itself. There's something both humbling and beautiful about this realization. The Earth spent hundreds of millions of years preparing itself for life, laying the chemical and physical groundwork for everything that would follow with infinite patience and no audience. This deep time perspective also helps us understand our place in the larger story of our planet. We humans have existed for perhaps 300,000 years, a span that represents only about 0.007% of Earth's total history. Our entire recorded history spans only about 5,000 years, roughly 0.0001% of Earth's history. Even if we include our entire lineage back to the first primates, we're talking about perhaps 60 million years, or about 1.3% of Earth's total history. The Hadean Eon alone, this period of fire and early cooling that we've been exploring, lasted more than 2,300 times longer than our entire species has existed. It's almost impossible to truly comprehend such timescales with our human minds, evolved as they are to deal with the rhythms of days and seasons and individual lifetimes. Yet, in another sense, we are intimately connected to this deep history. Every atom in your body was forged either in the nuclear furnaces of ancient stars or in the chemical laboratories of the early Earth. The carbon in your muscles, the iron in your blood, the calcium in your bones, all of these elements were cycling through the Earth system billions of years before the first life appeared. The water in your cells has been part of the global water cycle for billions of years. Some of those water molecules may have fallen as rain on the first solid ground, flowed in the first rivers, evaporated from the first shallow seas. In a very real sense, you are made of the early Earth. You are the Earth become conscious, the planet's matter organized in such a way that it can contemplate its own deep history. This perspective can be both dizzying and oddly comforting. Dizzying because it reminds us of how brief and recent our existence is in the context of planetary time. Comforting because it reminds us that we are part of something much larger and more enduring than ourselves. Participants in a story that began billions of years before we appeared, and will continue for billions of years after we're gone.
The early Earth's patience in preparing the conditions for life also offers us a kind of wisdom about change and transformation. The planet didn't rush its development. It took the time needed for each stage of the process to unfold completely before moving on to the next stage. There's something to be learned here about the value of patience.
of allowing processes to unfold in their own time, of trusting that slow, steady changes can lead to profound transformations. The legacy of fire. As the Hadean eon drew to a close, the Earth that emerged from those 700 million years of fire and transformation bore little resemblance to the molten ball of rock that had begun the journey. But the legacy of that fiery beginning would continue to shape our planet for billions of years to come, including today. The internal structure that formed during the Great Differentiation, the iron core, the rocky mantle, the thin crust, still characterizes our planet today. The magnetic field generated by the molten outer core still protects us from harmful solar radiation. The heat slowly leaking from the interior still drives the volcanic activity and plate tectonics that continue to reshape Earth's surface. The early atmosphere and ocean, though they would undergo dramatic changes as life evolved and oxygen accumulated, established the basic chemical cycles that still regulate our planet's climate. The water cycle, the carbon cycle, the weathering of rocks, and the transport of dissolved materials by rivers, all of these processes began during the Hadean and continued today. Perhaps most importantly, the complex chemistry that emerged in the hot, mineral-rich oceans of the early Earth established the chemical foundation for life itself. The amino acids, nucleotides, and other organic molecules that form the building blocks of living things are still made of the same elements, bonded in the same ways, that characterized the prebiotic chemistry of 4 billion years ago. When we look at the most ancient forms of life still existing on Earth today, the extremophiles, bacteria that live in hot springs, deep ocean vents, and other extreme environments, we're seeing organisms that may closely resemble the earliest life forms that emerged from the chemical soup of the Hadean Ocean. These organisms thrive in conditions of high temperature, acidity, and mineral concentration that would be lethal to most modern life, but that were probably typical of the early Earth. The early Earth also established patterns of resilience and recovery that would prove crucial throughout the planet's subsequent history. The Earth learned, during those early hundreds of millions of years, how to absorb massive shocks, asteroid impacts, volcanic catastrophes, dramatic changes in atmospheric composition, and still maintain the basic conditions necessary for complex chemistry and, eventually, life. This resilience would be tested many times throughout Earth's history. The planet would survive multiple episodes of global glaciation, massive volcanic eruptions, asteroid impacts that would wipe out most existing species, and dramatic changes in atmospheric composition. Each time, the fundamental systems established during the Hadean would help the planet recover and continue evolving. The early Earth also established the template for the kind of creative destruction that would characterize the planet's entire subsequent history. The constant cycle of volcanic creation and erosional destruction, the continuous recycling of materials between the surface and the interior, the dynamic balance between stability and change, all of these patterns were first established during the planet's fiery youth. Today, when we study the Earth system, the complex web of interactions between the atmosphere, oceans, solid Earth, and biosphere, we're studying a system whose basic architecture was laid down during the Hadean eon. The feedback loops that regulate global climate, the chemical cycles that transport materials around the planet, the energy flows that drive weather and geologic activity, all of these have their roots in the processes that began when the Earth was still a world of fire. Even our modern concerns about climate change and environmental degradation can be better understood in the context of deep Earth history. The planet has experienced dramatic climate changes before, including periods when the surface was far hotter than anything we're likely to experience due to human activities. The Earth system has demonstrated over and over again its ability to find new equilibria, new stable states that can persist for millions or hundreds of millions of years. This doesn't mean that climate change isn't a serious concern. The new equilibrium might be very different from the one we're accustomed to,
and the transition period could be difficult for many species, including humans. But it does provide perspective on the kinds of changes our planet is capable of surviving and adapting to.
The seeds of tomorrow. As the Hadean Eon came to an end around 3.8 billion years ago, the stage was set for the next great chapter in Earth's history, the emergence of life. But that emergence didn't happen overnight. It was the culmination of hundreds of millions of years of chemical evolution, the gradual organization of simple molecules into increasingly complex systems. The transition from the Hadean to the Archean Eon marked not just a change in geological classification, but a fundamental shift in the nature of Earth's surface environment. For the first time since the planet's formation, conditions were stable enough for truly complex chemistry to occur and persist over long periods of time. The ocean had cooled to temperatures where large, complex molecules could remain stable. The atmosphere had developed a relatively steady composition that wouldn't destroy delicate chemical structures. The crust had thickened enough to provide stable platforms for shallow water environments where chemistry could proceed without constant disruption from volcanic activity. Perhaps most importantly, the Earth had developed sufficient chemical complexity to support self-organizing systems, molecular networks that could maintain themselves, grow, and even reproduce their own structures. These weren't living systems yet, but they were systems that exhibited some of the key properties that would eventually characterize life. In the warm, mineral-rich pools at the edges of the ocean, complex organic molecules were beginning to organize themselves into primitive membranes, thin barriers that could separate the inside of a chemical system from the outside environment. These early membranes were probably made of simple fatty acids and other lipid molecules, but they represented a crucial step toward the cellular organization that characterizes all living things. Other complex molecules were beginning to exhibit catalytic properties, the ability to speed up specific chemical reactions. These early catalysts were probably much simpler than the protein enzymes that perform similar functions in modern cells, but they demonstrated that molecular systems could evolve the ability to control and direct their own chemistry. Perhaps most significantly, some molecular systems were beginning to exhibit primitive forms of information storage and reproduction. Simple sequences of nucleotides, the building blocks of modern DNA and RNA, could serve as templates for the formation of complementary sequences. This meant that chemical information could be copied and passed on to new generations of molecules. The combination of self-organization, catalysis, and information storage created the possibility of chemical systems that could evolve, that could change over time in response to environmental pressures, with successful variants becoming more common and unsuccessful variants disappearing. This chemical evolution was still very different from biological evolution. The molecules involved were much simpler than modern biological molecules. The processes were much slower and less efficient, and there was no clear boundary between living and non-living systems. But the fundamental principles were the same: variation, selection, and inheritance. Different molecular systems would form by chance. Some would be more stable or more successful at reproducing themselves than others. The successful systems would become more common over time, while unsuccessful systems would disappear. Over millions of generations of such chemical evolution, molecular systems gradually became more complex, more efficient, and more lifelike. Eventually, somewhere around 3.5 to 3.8 billion years ago, these systems crossed the threshold from complex chemistry to primitive life. The exact nature of that threshold is still debated by scientists and may always remain somewhat mysterious. Where do you draw the line between a very complex chemical system and a very simple living system? But regardless of where exactly you place that line, the crossing of it represented one of the most important events in Earth's history, the emergence of life from the chemical foundations laid down during the Hadean Eon. The Eternal Dance.
Today, as you sit listening to this story, the Earth continues the dance that began over 4.5 billion years ago. The same fundamental processes that characterized the Hadean Earth, the flow of heat from the interior to the surface, the circulation of water between the oceans and atmosphere, the chemical weathering of rocks, the cycling of elements through different reservoirs, all of these continue today, though in modified forms. The heat flow is much reduced from Hadean levels, but it still drives volcanic activity around the world. The Mid-Atlantic Ridge, where new ocean floor is constantly being created, is a direct descendant of the volcanic processes that built the first ocean basins. The Ring of Fire around the Pacific Ocean, with its spectacular volcanoes and frequent earthquakes, reflects the same kinds of crustal movements that shaped the early Earth. The water cycle continues to transport vast amounts of material around the planet, though today it's mediated by biological processes that didn't exist in the Hadean. Plants and animals participate in the water cycle, modifying the chemistry of rainwater and groundwater in ways that the early Earth couldn't have imagined. The chemical weathering of rocks continues to regulate Earth's climate, though today this process is complicated by the presence of life and by human activities. The same basic chemical reactions that began neutralizing the early Earth's acid atmosphere continue to remove carbon dioxide from the modern atmosphere, helping to stabilize global temperatures over geological timescales.
Even the magnetic field that protects us from solar radiation is generated by the same convection currents in the liquid outer core that began during the Earth's early differentiation. The iron that sank to form our planet's core during the Hadean continues to flow in great currents that create and maintain the magnetic field that makes complex life possible on Earth's surface. In a very real sense, we are still living on the Hadean Earth. Or rather, we are living on what the Hadean Earth became after 4.5 billion years of evolution and development. The atoms in our bodies, the ground beneath our feet, the air we breathe, the water we drink, all of these have been part of Earth's system since the very beginning, cycling endlessly through different forms and combinations. The carbon atoms in your body may once have been part of the early atmosphere, or dissolved in the Hadean Ocean, or locked up in ancient rocks that have since been weathered away. The iron in your blood definitely spent billions of years in the Earth's core before being brought to the surface by volcanic activity and incorporated into the biosphere. We are not separate from the Earth system. We are part of it. Temporary arrangements of Earth's atoms and molecules, temporary patterns in the flow of Earth's materials and energy. Our consciousness, our ability to contemplate our own origins and our planet's history, represents something genuinely new in Earth's evolution. As far as we know, the first time the planet has developed the ability to understand itself. But even this consciousness is built from the same materials and follows the same fundamental principles that have characterized Earth's evolution from the very beginning. The electrical impulses in our brains obey the same physical laws that governed the behavior of charged particles in the early solar nebula. The chemical reactions in our cells are variations on the same themes that characterized the prebiotic chemistry of the Hadean Ocean. This perspective, seeing ourselves as part of Earth's ongoing evolution rather than separate from it, can profoundly change how we think about our relationship with our planet. We are not visitors to Earth, not colonists who happen to end up here by accident. We are Earth, in the same way that a wave is part of the ocean, or a flame is part of a fire. The Earth that began as a ball of molten rock has become, through us, capable of love, art, music, mathematics, and wonder. The matter that once flowed as lava now flows as blood through our veins, carries thoughts through our brains, forms the words with which we tell each other stories about where we came from and where we're going. Epilogue, the continuing story. As we come to the end of our journey through the Hadean Eon, it's time to draw the threads of our story together and reflect on what it means for us, here in the present moment, to carry this deep history within us. The story we've told tonight is not just ancient history. It's the foundation story of everything we are and everything we know. Every breath you take contains atoms that were once part of the early Earth's atmosphere. Every drop of water you drink has been cycling through the Earth's system for billions of years, falling as rain on landscapes that existed before life began. The ground you walk on is made of rocks that formed through processes that began in the Hadean Eon. The metals in your smartphone, the silicon in your computer, the minerals in your bones, all of these materials were forged in the high-temperature, high-pressure environment of the early Earth. But more than just sharing materials with the ancient Earth, we share processes. The same physical and chemical laws that governed the behavior of the early Earth still govern our bodies today. The flow of energy that once drove convection currents in the global magma ocean now drives the circulation of blood through our bodies. The chemical reactions that once organized simple organic molecules in primordial tide pools now organize the complex biochemistry of our cells. In a profound sense, we are the Earth's way of knowing itself. The same matter that once flowed unconsciously as molten lava has organized itself over billions of years of evolution into forms capable of consciousness, memory, and understanding. Through us, the Earth can contemplate its own history, marvel at its own complexity, and imagine its own future. This realization carries with it both wonder and responsibility. Wonder at the extraordinary journey that brought us here, the billions of years of planetary evolution that transformed a ball of molten rock into a world capable of supporting consciousness and beauty and love. Responsibility because we are now active participants in Earth's continuing evolution, not just passive beneficiaries of its long history. The choices we make today will influence the Earth's trajectory for millions of years to come. The carbon we release into the atmosphere, the species we drive to extinction or help to preserve, the technologies we develop and the ways we use them, all of these will become part of Earth's deep history, woven into the ongoing story that began 4.5 billion years ago. But this responsibility need not be a burden. It can instead be a source of meaning and connection. We are not isolated individuals struggling alone against an indifferent universe. We are part of something much larger and more enduring than ourselves, participants in the greatest story ever told, the story of how the universe evolved the capacity to understand itself. The early Earth teaches us about patience and persistence. The planet spent hundreds of millions of years laying the groundwork for life with no guarantee that life would ever appear. Yet the processes continued. The chemistry grew more complex. The conditions slowly became more suitable until eventually the impossible happened and life emerged. Perhaps there's wisdom here for our own lives and our own challenges. The problems we face, whether personal or collective, may not have quick solutions. But if we persist, if we continue working toward positive change, if we trust in the slow processes of growth and development, seemingly impossible transformations can occur. The early Earth also teaches us about resilience. The planet survived countless catastrophes during its early history. Asteroid impacts that would have sterilized the surface, volcanic eruptions that filled the atmosphere with toxic gases, dramatic changes in climate that would have been lethal to any complex life. Yet the fundamental systems persisted, adapted, and eventually flourished. This resilience wasn't built into the Earth from the beginning. It was developed gradually through billions of years of trial and error, crisis, and recovery. Each challenge that the planet survived made it better equipped to handle future challenges. Perhaps we can apply this lesson to our own lives and societies, building resilience not by avoiding difficulties, but by learning how to adapt and recover from them. Most importantly, the story of the early Earth reminds us that we are part of something much larger than ourselves. The atoms in our bodies have been part of Earth's story since the very beginning. The water in our cells has been flowing through the planetary system for billions of years. The energy that powers our thoughts and emotions ultimately derives from the same nuclear processes that power the sun and heated the early Earth. We are not separate from nature. We are nature. We are not observers of the Earth system. We are the Earth system become conscious of itself. This realization can transform how we see our place in the world and our relationships with all other forms of life. Tonight, as you prepare for sleep, take a moment to feel your connection to this deep history. Feel the solid ground beneath you, ground that was once molten lava, that has been cooling and solidifying for billions of years to provide you with a stable foundation. Feel the air entering your lungs, air that has been cycled through the Earth system countless times, that connects you to every other breathing thing that has ever lived. Feel the water in your body, water that may have once fallen as the first rain on the first solid ground, that has flowed in ancient rivers and evaporated from primordial seas. Feel your heartbeat, a rhythm that echoes the deep rhythms of planetary evolution, the slow pulse of geologic time that continues within each of us. You are made of stardust and ancient seas, of volcanic fire and the patient work of time. You carry within your body and your consciousness the entire history of our planet, from its fiery birth to this present moment. You are a temporary arrangement of ancient materials, a brief flame of consciousness in the long story of Earth's evolution. But temporary does not mean insignificant. Every moment of awareness, every act of kindness, every flash of understanding or burst of creativity adds something new to the universe's growing capacity for consciousness and connection. Through us, the cosmos continues to evolve, to become more complex, more aware, more capable of love and wonder. The story that began 4.5 billion years ago with a ball of molten rock continues today through each of us. Every breath we take, every thought we think, every relationship we form is part of Earth's ongoing evolution. We are not the end point of this story. We are participants in a narrative that will continue for billions of years to come, taking forms we can barely imagine. So rest now, knowing that you are part of the greatest story ever told. Dream of molten seas and cooling stone, of the first rains falling on volcanic slopes, of complex molecules organizing themselves in tide pools warmed by the Earth's internal fire. Dream of the patient work of time and chemistry that made your existence possible. And when you wake tomorrow, remember that you carry this deep history within you. You are not just a human being living on Earth. You are Earth become human, the planet's matter organized in such a way that it can contemplate its own magnificent history and help write the chapters yet to come. The lava Earth still glows within us all, transformed but never truly extinguished, continuing its ancient dance in new forms, forever reaching toward greater complexity, greater consciousness, greater connection. The fire that once lit our world from within now burns as the spark of life and awareness within each of us. The Silent Witnesses. There are places on Earth today where you can still touch the Hadean world, still hold pieces of that ancient fire in your hands. These are not dramatic places. No towering volcanoes or spectacular canyons mark their locations. They are quiet places, humble places,
where patient scientists have learned to read the whispers of deep time preserved in the smallest fragments of the ancient world. In the remote hills of Western Australia, in a place called Jack Hills, lie some of the most precious objects on Earth. To the untrained eye, they look like nothing special, tiny grains of sand mixed in with ordinary sedimentary rocks. But these grains are zircon crystals, and some of them are 4.4 billion years old, making them the oldest pieces of Earth that we can still touch today.
The zircon crystal in your hand was there when the first oceans condensed from the atmosphere. It was there when life first emerged in those ancient seas. It was there when the first continents rose above the waves, when the first plants colonized the land, when the first animals left the sea to walk on dry ground. It witnessed the age of dinosaurs, their extinction, the rise of mammals, the evolution of humans, and all of recorded history. But this crystal doesn't just passively remember the past, it actively records it. Locked within its crystal structure are tiny inclusions of other minerals, chemical signatures that can tell us about the conditions under which it formed. The ratios of different isotopes in the crystal can tell us the temperature of the magma from which it crystallized. The presence of certain trace elements can tell us about the composition of the early atmosphere and ocean. Most remarkably, some zircon crystals contain tiny inclusions of water, actual H2O molecules that were trapped when the crystal formed 4.4 billion years ago. This water is a direct sample of the Hadean Ocean, preserved for all this time in a microscopic time capsule. When scientists analyze this ancient water, they can determine the temperature and chemical composition of the earliest oceans, giving us our most direct evidence of what conditions were like on the young Earth. Other ancient witnesses exist as well, though they require even more sophisticated detective work to recognize. In Greenland, some of the world's oldest rocks, 3.8 billion years old, preserve chemical signatures that hint at the presence of life almost as far back as the end of the Hadean Eon. The ratios of different carbon isotopes in these rocks suggest that biological processes were already at work, selectively concentrating certain types of carbon in ways that only living organisms can do. These rocks also preserve evidence of the Earth's early magnetic field, locked in the orientation of magnetic minerals that formed when the rocks were still hot. By studying these ancient magnetic signatures, scientists can reconstruct the strength and orientation of the Earth's magnetic field billions of years ago, helping us understand how the planet's protective magnetic shield developed over time. Even more subtle are the chemical signatures preserved in the oldest meteorites, rocks that formed in the same solar nebula as Earth but were never incorporated into a large planet. These meteorites preserve the original composition of the materials from which Earth formed, allowing scientists to work backward from the present composition of our planet to understand how the process of planetary differentiation changed the distribution of elements between Earth's core, mantle, and crust. Perhaps the most poetic of these ancient witnesses are the noble gases, helium, neon, argon, krypton, and xenon, trapped in ancient rocks and minerals. These gases are chemically inert, meaning they don't react with other elements or participate in chemical weathering. Once trapped, they remain unchanged for billions of years, preserving perfect samples of the ancient atmosphere. Different isotopes of these gases have different origins. Some come from the solar nebula, others are produced by radioactive decay, still others are created by cosmic ray bombardment. By analyzing the ratios of these different isotopes in ancient rocks, scientists can reconstruct the evolution of Earth's atmosphere from the very beginning, tracking how it changed as the planet outgassed, as water condensed and fell as rain, as life evolved and began to modify atmospheric composition. These ancient witnesses remind us that the past is not truly gone. It lives on in the rocks beneath our feet, in the crystals we find on beaches, in the very atoms that make up our bodies.
The Hadean Earth is not just a story we tell about the distant past, it's a reality that continues to exist all around us, preserved in countless tiny fragments, waiting for those with the knowledge and patience to read its ancient messages. Chapter 22: The Language of Stones. Learning to read the language of stones is perhaps humanity's most remarkable intellectual achievement. For most of our species' existence, rocks were simply part of the landscape, useful for tools and building materials, but silent about their origins and history. It's only in the last few centuries that we've developed the ability to make stones speak, to coax from them the stories of worlds and times unimaginably remote from our daily experience. This language is written not in words, but in chemistry, not in sentences, but in crystal structures, not in paragraphs, but in the layered relationships between different types of rocks. It's a language where a tiny variation in the ratio of two isotopes can reveal the temperature of an ancient ocean, where the orientation of magnetic crystals can tell us about the strength of the Earth's magnetic field billions of years ago, where the presence of certain rare elements can indicate whether a rock formed in the presence of water or in a completely dry environment.
Consider how scientists learned to read the age of rocks, one of the fundamental skills needed to understand Earth's history. The key insight was realizing that certain elements are naturally radioactive, meaning their atomic nuclei are unstable and decay into other elements at perfectly predictable rates. Uranium-238, for example, decays into lead-206 with a half-life of 4.47 billion years, meaning that in any sample of uranium-238, exactly half the atoms will have decayed into lead after 4.47 billion years. This provides a perfect natural clock. When a zircon crystal forms from cooling magma, it incorporates small amounts of uranium into its crystal structure but excludes lead. Over time, as the uranium atoms decay, lead atoms accumulate in the crystal. By measuring the ratio of uranium to lead in an ancient crystal, scientists can calculate exactly how long the decay process has been occurring, which tells them precisely when the crystal formed. But this radioactive clock is just one word in the language of stones. The presence of certain minerals can tell us about temperature and pressure conditions. Diamonds, for example, only form under the extreme pressures found deep in the Earth's mantle. So finding diamonds in a rock tells us that it has been to great depths and returned to the surface. Certain types of garnet only form at specific combinations of temperature and pressure, allowing geologists to reconstruct the conditions under which ancient rocks formed. The chemistry of volcanic rocks can tell us about the composition of the mantle from which they came. Different types of magma have characteristic signatures. Some are rich in silica and form light-colored viscous lavas. Others are poor in silica and form dark, fluid basalts. By analyzing the chemical composition of ancient volcanic rocks, scientists can reconstruct the evolution of the Earth's mantle over billions of years. Even more subtle are the isotopic signatures that can reveal information about ancient environmental conditions. The ratio of oxygen-18 to oxygen-16 in ancient rocks depends on the temperature at which the rocks formed. The warmer the conditions, the more oxygen-18 gets incorporated. This isotopic thermometer works because different isotopes of oxygen behave slightly differently in chemical reactions, with the differences being more pronounced at lower temperatures. Similarly, the ratio of sulfur isotopes can reveal information about the composition of the ancient atmosphere. In today's oxygen-rich atmosphere, sulfur isotopes are processed by photochemical reactions that create characteristic patterns. But in the oxygen-free atmosphere of the early Earth, these reactions couldn't occur, creating different isotopic signatures. By studying sulfur isotopes in rocks of different ages, scientists can determine when oxygen first appeared in Earth's atmosphere, one of the most important transitions in our planet's history. The language of stones even includes information about ancient life. Certain minerals only form in the presence of living organisms. For example, some types of limestone are made almost entirely of the shells of ancient sea creatures. The carbon isotopes in ancient rocks can reveal the presence of biological processes, since living organisms preferentially use lighter carbon isotopes, leaving characteristic signatures in the geological record. Perhaps most remarkably, scientists have learned to read the magnetic language preserved in ancient rocks. When volcanic rocks cool, magnetic minerals within them align themselves with the Earth's magnetic field, like tiny compass needles freezing in place. Over geological time, as the continents drift and the magnetic field changes, these frozen compasses preserve a record of where the rock was located and what the magnetic field was like when it formed. This paleomagnetic record has revealed that the Earth's magnetic field has reversed many times throughout history, the North Magnetic Pole becoming the South Magnetic Pole and vice versa. It's also revealed the history of continental drift, showing how the continents have moved around the globe over hundreds of millions of years. Some rocks formed near the equator are now found near the poles and vice versa, telling the story of the Earth's dynamic surface. But perhaps the most poetic aspect of the language of stones is what it tells us about deep time itself. Every rock is a library, containing multiple stories written at different times and in different languages. A single outcrop might contain rocks that formed billions of years ago, intruded by magma that solidified hundreds of millions of years later, folded and faulted during mountain-building events, and finally exposed to the surface by recent erosion. Learning to read these superimposed stories requires patience and careful observation. Geologists must learn to see the relationships between different rock layers, to recognize which events came first and which came later, to untangle the complex history written in stone. It's detective work on a cosmic scale, piecing together evidence of events that occurred over timescales that dwarf human comprehension. Chapter 23. The Theater of Elements. Music becomes more dramatic and orchestral, with different instrumental sections representing different elements. In the great theater of the early Earth, each chemical element played its own unique role, bringing its own characteristics and capabilities to the cosmic drama unfolding on our planet's surface. Understanding these elemental personalities, their preferences, their behaviors, their interactions with each other, is crucial to understanding how the complex chemistry of the Hadean Earth gave rise to the conditions necessary for life. Silicon, one of the most abundant elements in the Earth's crust, was perhaps the most important actor in determining the physical stage on which this chemical drama would unfold. Silicon has a special affinity for oxygen, forming strong silicon-oxygen bonds that create the framework of most rock-forming minerals. Silicate minerals, compounds of silicon, oxygen, and various other elements, make up more than 90% of the Earth's crust. But silicon's role went beyond just forming rocks. The way silicon atoms bond with oxygen create three-dimensional framework structures that can incorporate many other elements. This made silicate minerals excellent hosts for other elements, creating a diverse array of mineral types with different properties and different capabilities for participating in chemical reactions. The behavior of silicon was also crucial in determining the viscosity of magmas. Magmas rich in silicon are thick and sticky, flowing slowly and trapping gases that can lead to explosive volcanic eruptions. Magmas poor in silicon are thin and fluid, flowing readily and allowing gases to escape easily, leading to gentler effusive eruptions. During the Hadean Eon, when volcanic activity was much more widespread than today, the silicon content of magmas helped determine the style and intensity of volcanic events across the planet. Iron, another abundant element, played equally important roles but with very different characteristics. Iron is what chemists call a transition metal, meaning it can exist in multiple oxidation states, different configurations of electrons that give it different chemical properties. In the oxygen-poor environment of the early Earth, iron existed primarily in its reduced form, making it highly reactive and able to participate in a wide variety of chemical reactions.
Iron's magnetic properties were also crucial during this period.
As iron-rich magmas cooled and solidified, magnetic iron minerals would align themselves with the Earth's magnetic field, creating a permanent record of the field's strength and direction. This paleomagnetic record, preserved in Hadean Age rocks, provides some of our best evidence for the early development of Earth's magnetic field. But perhaps iron's most important role was biological. Iron-sulfur minerals, common in the reducing environment of the early Earth, have chemical properties that make them excellent catalysts for organic reactions. Some scientists believe that iron-sulfur minerals on the early ocean floor may have served as primitive metabolisms, catalyzing the formation of complex organic molecules from simple ingredients. Iron remains essential to life today. It's at the heart of hemoglobin molecules that carry oxygen in our blood, and it's crucial to many of the enzymes that power cellular metabolism. Carbon, though much less abundant than silicon or iron, was the element that would ultimately make the transition from geochemistry to biochemistry possible. Carbon has unique bonding properties that allow it to form long chains, branched networks, and complex three-dimensional structures. These properties make carbon the ideal foundation for the large, complex molecules that life requires. In the reducing atmosphere of the early Earth, carbon could form bonds with hydrogen to create methane, with nitrogen to create hydrogen cyanide, and with other carbon atoms to create increasingly complex hydrocarbons. These simple carbon compounds could then serve as building blocks for more sophisticated organic molecules, amino acids, sugars, nucleotides, and eventually the proteins and nucleic acids that form the basis of all known life. But carbon's role wasn't limited to organic chemistry. Carbon dioxide, one of the most important gases in the early atmosphere, played a crucial role in regulating planetary temperature through the greenhouse effect. The balance between carbon dioxide in the atmosphere and dissolved carbonate minerals in the ocean was one of the key feedback mechanisms that helped stabilize Earth's climate during its early evolution. Sulfur, often overlooked in popular accounts of planetary chemistry, was equally important during the Hadean Eon. Volcanic activity was constantly adding sulfur compounds to the atmosphere and ocean, where they could participate in a wide variety of reactions. Hydrogen sulfide, sulfur dioxide, and other sulfur gases made the early atmosphere quite different from today's relatively sulfur-poor air. But sulfur's importance went beyond its abundance. Sulfur-containing molecules have unique chemical properties that make them particularly useful for complex chemistry. Many of the key molecules in modern biochemistry, including some amino acids, vitamins, and enzymes, contain sulfur atoms that are crucial for their function. Some scientists believe that sulfur chemistry may have been even more important than carbon chemistry in the earliest stages of life's evolution. Phosphorus, though much rarer than the other elements we've discussed, was crucial because of its role in energy storage and transfer. Phosphorus-containing molecules like ATP, adenosine triphosphate, are the universal energy currency of modern life. The early Earth's volcanic activity was gradually releasing phosphorus from the planet's interior, making it available for incorporation into increasingly complex molecules. But phosphorus presented a challenge as well as an opportunity. Most phosphorus on Earth is locked up in insoluble minerals that don't readily dissolve in water. Making phosphorus available for biological chemistry required special conditions, perhaps the hot, acidic water near hydrothermal vents, or the evaporation of shallow pools that could concentrate dissolved phosphorus to high levels. Nitrogen, abundant in today's atmosphere, but probably much rarer in the early Earth's atmosphere, was important for the formation of amino acids and nucleic acids. But molecular nitrogen, N2, is very stable and unreactive under normal conditions. Converting it into forms that could participate in organic chemistry required high-energy processes, lightning, volcanic activity, or bombardment by ultraviolet radiation. Each of these elements brought its own possibilities and limitations to the chemical evolution occurring on the early Earth. The interplay between their different properties, silicon's structure-building capabilities, iron's catalytic properties, carbon's complexity-generating potential, sulfur's chemical versatility, phosphorus's energy-handling abilities,
Nitrogen's structural importance created a rich chemical landscape where increasingly sophisticated molecular systems could evolve. Understanding these elemental personalities helps us appreciate why life evolved the way it did and why it requires such specific conditions to thrive. Life as we know it is not just a product of any chemistry. It's a product of the specific chemical possibilities that exist when these particular elements interact under the particular conditions that existed on the early Earth. Chapter 24, The Rhythm of Catastrophe and Recovery. Music alternates between dramatic, chaotic sections and gentle, rebuilding themes. One of the most important lessons that the early Earth teaches us is about resilience. Not the kind of resilience that avoids disruption, but the kind that learns to recover from catastrophic change and emerge stronger and more complex than before. The Hadean Earth was not a stable, peaceful world, slowly and steadily evolving toward life. It was a world of repeated catastrophes, each one so severe that it might have ended the story entirely, yet each one ultimately contributing to the conditions that made life possible. The most dramatic of these catastrophes were the massive asteroid and comet impacts that characterized the late heavy bombardment period, roughly 4.1 to 3.8 billion years ago. These were not the relatively small impacts that occasionally strike Earth today. These were world-shaking events that could vaporize entire oceans and melt the planet's crust to depths of hundreds of miles. Imagine the largest impact of this period, perhaps an asteroid 200 kilometers across, moving at 20 kilometers per second, carrying the kinetic energy of billions of nuclear weapons. When such an object struck the early Earth, the energy release would have been almost incomprehensible. The impact would have created a crater thousands of kilometers across and thrown molten rock and vaporized seawater completely around the globe. For months or years after such an impact, the Earth's surface would have been uninhabitable. The atmosphere would have been filled with vaporized rock and superheated steam. Any ocean would have boiled away completely, leaving the planet temporarily dry. The surface temperature would have risen to over 1,000 degrees Celsius, hot enough to melt lead, hot enough to sterilize any complex chemistry that had been developing in cooler environments. Yet remarkably, the Earth recovered from each of these catastrophic events. The vaporized oceans would gradually recondense as the planet cooled. The molten surface would solidify into new crust. Chemical evolution would begin again, starting from simpler building blocks, but incorporating the lessons learned from previous cycles. Each cycle of destruction and recovery was not just a return to previous conditions. It was an opportunity for the planet to experiment with new configurations, new chemical pathways, new environmental conditions. The massive impacts would bring new materials to the surface from the deep interior. They would create new types of rocks and minerals. They would reset the chemical composition of the atmosphere and ocean, providing new starting points for chemical evolution. Perhaps most importantly, each catastrophe would test the resilience of whatever chemical systems had evolved up to that point. Systems that could survive extreme conditions, high temperatures, radiation, chemical disruption, would persist and potentially multiply when conditions improved. Systems that were more fragile would disappear, but their component molecules might be recycled into new, potentially more robust arrangements. This process of catastrophic selection may have been crucial to the eventual emergence of life. Only chemical systems that could survive repeated cycles of destruction and recovery would persist long enough to develop the complex, self-organizing properties that characterize living systems. Life, in other words, may have been forged in catastrophe, developing its remarkable resilience through billions of years of surviving the unsurvivable. But catastrophes came in many forms, not just asteroid impacts. Massive volcanic eruptions could also reset large portions of the Earth's system. During the Hadean, volcanic activity was much more intense than it is today. Single volcanic events might cover areas the size of modern countries with molten rock,
fundamentally altering local environmental conditions. These volcanic catastrophes had different effects than impact events. Rather than cooling and sterilizing the environment, they typically heated it even further, adding new gases to the atmosphere and new dissolved materials to the ocean. They created new types of chemical environments: superheated water rich in dissolved minerals, gas-rock interfaces where catalytic chemistry could occur, temperature gradients that could drive complex reactions. Climate catastrophes were another type of disruption that shaped the early Earth. The planet's climate during the Hadean was probably quite unstable, subject to dramatic swings between hot and cold periods. These climate changes were driven by variations in volcanic activity, changes in atmospheric composition, and the gradual cooling of the planet's interior. During cold periods, much of the ocean might freeze, dramatically reducing the volume of liquid water available for chemical evolution. During hot periods, the enhanced greenhouse effect might drive surface temperatures so high that only the most heat-tolerant chemical processes could continue. Each climate swing would favor different types of chemistry and different types of molecular organization.
Perhaps most subtly, the early Earth experienced repeated cycles of atmospheric change as different gases were added and removed by geological and chemical processes. The composition of the atmosphere would determine which types of chemical reactions could occur, which molecules would be stable, and which energy sources would be available to drive chemical evolution. Through all of these catastrophes, impacts, volcanism, climate swings, atmospheric changes, the fundamental processes of chemical evolution continued. Each disruption was also an opportunity. Each catastrophe was also a creative event. The early Earth was learning, through trial and error on a planetary scale, how to build and maintain complex chemical systems in a hostile and unstable environment. This perspective on catastrophe and recovery offers profound insights for our own lives and our own times. We often think of disruption as purely negative, as something to be avoided or minimized. But the story of the early Earth suggests that disruption can also be creative, that catastrophe can be a necessary part of the process by which complex, resilient systems emerge. The chemical systems that eventually gave eyes to life were not the products of stable, protected environments. They were the survivors of billions of years of planetary catastrophe, tested and refined by conditions that would have destroyed anything less robust. Their resilience was earned through experience, developed through countless cycles of destruction and recovery. Chapter 25. The Dance of Energy and Information. Music becomes more intricate and layered, suggesting the flow of energy and the encoding of information. As the Hadean eon progressed and the Earth's chemical systems grew more sophisticated, two fundamental themes began to emerge that would eventually characterize all living systems: the flow of energy and the storage of information. These twin processes, energetics and informatics, would prove to be the twin pillars on which life would eventually be built. Energy, in the context of early Earth chemistry, meant the ability to drive chemical reactions that wouldn't occur spontaneously. Many of the reactions that build complex molecules from simple ones require an input of energy. They are what chemists call endergonic reactions. Without energy sources to drive these uphill reactions, chemistry would inevitably slide downhill towards simpler, more stable configurations. The early Earth was blessed with abundant energy sources. The planet's interior was much hotter than today, providing thermal energy that could drive high-temperature chemistry. Radioactive decay was more intense, providing both heat and high-energy radiation. Lightning was probably more common in the thick, turbulent atmosphere. And most importantly, the sun provided a constant stream of ultraviolet radiation that could break apart molecules and provide the energy needed to forge new bonds. But energy by itself is not enough to build complex systems. Energy must be harnessed, controlled, and directed. This requires what we might think of as molecular machinery.
systems that can capture energy from the environment and use it to drive specific reactions in specific directions. On the early Earth, the first such molecular machinery was probably very simple, perhaps just catalytic mineral surfaces that could channel energy from hydrothermal vents into particular types of organic synthesis. But even these primitive energy conversion systems represented a crucial step toward life. Modern living cells are essentially sophisticated energy processing machines. They capture energy from sunlight or from chemical reactions, store it in molecules like ATP, and then use it to drive the thousands of chemical reactions that keep the cell alive and growing. This energy processing is so fundamental to life that some scientists define life primarily in terms of its ability to capture and use energy to maintain complex organized structures. But energy processing alone is still not sufficient for life. Complex systems also need information, ways of storing and transmitting the instructions that determine how the system is organized and how it behaves. Without storage and transmission, each generation of a complex system would have to reinvent itself from scratch. On the early Earth, the first forms of information storage were probably very simple, perhaps just the shapes of catalytic molecules that could promote their own formation. If a particular molecular configuration was especially good at catalyzing the reactions that produced more molecules of that same configuration, then that configuration would tend to become more common over time. This represents a primitive form of heredity, the passing on of structural information from one generation of molecules to the next. It's not yet the sophisticated genetic code that modern life uses, but it's a crucial first step toward systems that can evolve and improve over time. The interaction between energy and information creates the possibility of chemical evolution, changes in molecular populations over time driven by differential success in capturing and using energy to maintain complex structures. Molecular configurations that are better at processing energy and storing information will tend to become more common, while less successful configurations will disappear.
Over millions of generations of such chemical evolution, molecular systems gradually became more sophisticated. They developed better ways of capturing energy, more efficient ways of storing information, and more complex ways of using energy to build and maintain organized structures. Perhaps most importantly, they began to develop what we might call metabolic networks, interconnected sets of chemical reactions that could sustain themselves and grow. In a metabolic network, the products of some reactions serve as the starting materials for other reactions, creating cycles that can continue indefinitely as long as energy and raw materials are available. The earliest metabolic networks were probably much simpler than the biochemical networks that power modern cells, but they represented a crucial conceptual breakthrough. For the first time, chemical systems could maintain themselves over extended periods, growing and reproducing without needing to be constantly rebuilt from scratch. These early metabolic networks also began to show primitive forms of regulation, ways of controlling which reactions occurred when and at what rates. If the concentration of a particular molecule became too high, it might inhibit the reactions that produced it, creating negative feedback that helped maintain stable concentrations. If the concentration became too low, the inhibition would be relieved, allowing production to resume. Such regulatory mechanisms allowed early chemical systems to maintain homeostasis, stable internal conditions despite changes in the external environment. This ability to maintain internal stability in the face of external change is another hallmark of living systems, and its emergence during the late Hadean was probably crucial to the eventual transition from chemistry to biology. The dance between energy and information also created the possibility of adaptation, the ability of chemical systems to modify their behavior in response to environmental changes. Systems that could adjust their energy processing strategies to take advantage of new energy sources or modify their information storage mechanisms to preserve crucial instructions under changing conditions would have significant advantages over less adaptable systems.
Through millions of years of chemical evolution, driven by the constant interplay between energy processing and information storage, the late Hadean Earth developed chemical systems of remarkable sophistication, systems that could maintain themselves, grow, reproduce, evolve, and adapt to changing conditions. These systems were not yet alive in the full biological sense, but they had developed many of the key properties that would eventually characterize living things. They had learned to dance the complex dance of energy and information that powers all life, and they had set the stage for the emergence of the first true organisms during the subsequent Archean Eon. Chapter 26. The Poetry of Possibility. As we approach the very end of our journey through the Hadean Eon, it's worth reflecting on one of the most remarkable aspects of this entire story: the way that purely physical and chemical processes, operating according to simple natural laws, gave rise to systems of almost unimaginable complexity and beauty. When we look at the early Earth from the perspective of pure physics, it might seem like a simple system: hot rock cooling in space, following the basic laws of thermodynamics and fluid dynamics. Heat flows from hot places to cold places. Dense materials sink, light materials rise. Chemical reactions proceed according to the principles of thermodynamics and kinetics. Nothing in these basic laws seems to predict the emergence of the complex, organized information processing systems that would eventually become life. Yet somehow these simple laws, operating over vast timescales in the rich chemical environment of the early Earth, generated exactly such systems. The universe, it seems, has an inherent tendency toward complexity, toward organization, toward the emergence of systems that are greater than the sum of their parts. This emergence of complexity from simplicity is one of the deepest mysteries in science, and also one of its most beautiful insights. We see it not just in the origin of life, but throughout the natural world. Simple rules governing the behavior of individual birds give rise to the complex, coordinated movements of flocks. Simple interactions between neurons give rise to consciousness and thought. Simple gravitational attractions between particles of dust and gas give rise to stars, planets, and galaxies. The early Earth was a laboratory for exploring these principles of emergence on a planetary scale. Every process we've discussed in our journey through the Hadean Eon represents an example of how simple laws can generate complex outcomes when given sufficient time and space to operate. Perhaps most remarkably, many of these emergent properties seem to be almost inevitable given the right starting conditions. Complex organic molecules form spontaneously when simple gases are exposed to energy sources. Self-organizing chemical systems arise naturally when complex molecules are concentrated in appropriate environments. Catalytic networks develop automatically when diverse molecular populations interact over extended periods of time. This suggests that the emergence of life might not have been an incredibly unlikely accident, but rather a natural consequence of the laws of chemistry and physics operating in the kind of environment that the early Earth provided. If so, then life might be a common feature of planetary evolution throughout the universe, arising wherever planets provide the right combination of chemical diversity, energy sources, and stable environments over sufficient timescales.
The story of the Hadean Earth also illustrates the power of deep time to transform the seemingly impossible into the inevitable. Individual chemical reactions that have almost infinitesimally small probabilities of occurring can become virtually certain when given billions of opportunities over millions of years. Molecular configurations that would be impossibly unlikely to arise by pure chance can emerge naturally through processes of chemical evolution that gradually increase their probability of formation. This perspective on deep time and emergence offers a kind of wisdom that transcends the specific scientific details of planetary formation. It suggests that transformation and growth are possible even when they seem impossible, given sufficient patience and persistence. Complex problems that seem intractable on short timescales may yield to gentle, sustained effort over longer periods.
The early Earth's patient construction of the chemical foundations for life also illustrates the interconnectedness of all natural processes. The formation of the first solid crust was connected to the development of the magnetic field. The cooling of the surface was connected to the evolution of the atmosphere. The emergence of complex chemistry was connected to the cycles of volcanic activity and crustal recycling. Every process influenced every other process, creating a web of feedbacks and interactions that shaped the planet's evolution in ways that no single process could have achieved alone. This systems-level thinking, seeing the Earth as an integrated whole rather than a collection of separate parts, has become increasingly important in modern science and offers valuable insights for understanding complex challenges in our own time. Perhaps most importantly, the story of the Hadean Earth reminds us that we are part of something much larger and more enduring than ourselves. The atoms in our bodies, the energy that powers our thoughts, the chemical processes that sustain our lives, all of these have their origins in the cosmic and planetary processes we've been exploring. We are not separate from the natural world. We are expressions of it, temporary arrangements of matter and energy that have emerged from the same processes that shaped the early Earth. Our consciousness, our creativity, our capacity for love and wonder, these represent new chapters in the same great story of emergence and complexity that began with the first cooling of molten rock and the first complex molecules in primordial seas. In contemplating the deep history of our planet, we gain a perspective on our own place in the cosmic story. We are neither insignificant accidents in an indifferent universe, nor the predetermined goal toward which all evolution has been leading. We are participants in an ongoing process of emergence and creativity that began billions of years ago and continues today through our choices, our relationships, and our contributions to the ongoing story of life on Earth. The poetry of possibility that characterizes the Hadean Earth continues to operate today, in our own lives and in the life of our planet. The same principles that transformed a ball of molten rock into a world capable of supporting consciousness continue to operate, creating new possibilities, new forms of organization, new expressions of the universe's inherent creativity. Chapter 27. The Eternal Return. Music develops cyclical themes, with melodies that return and develop, suggesting the ongoing nature of planetary processes. As our exploration of the Hadean Eon draws to a close, we find ourselves confronting a profound paradox. The story we've been telling is both ancient history and immediate present reality. The processes that shaped the early Earth didn't end when the Hadean Eon concluded 3.8 billion years ago. They continue today in modified forms as part of the ongoing evolution of our planet. The heat flow that drove convection in the early magma ocean still drives convection in Earth's mantle today, powering the movement of tectonic plates and the formation of new volcanic islands. The chemical weathering that began when the first acidic rains fell on cooling lava continues today, slowly dissolving mountains and carrying their dissolved remnants to the sea. The water cycle that began when the first oceans condensed from the atmosphere continues today, moving water between the air, land, and sea in an endless circulation that connects all parts of the Earth system. Even the complex chemistry that began in the mineral-rich pools and hydrothermal vents of the early Earth continues today, though now it's primarily mediated by living organisms. The same chemical elements that participated in prebiotic synthesis 4 billion years ago — carbon, hydrogen, oxygen, nitrogen, sulfur, phosphorus — continue to cycle through the biosphere, being incorporated into living tissues, released back to the environment, and recycled into new forms of life. In a very real sense, we are still living on the Hadean Earth.
The fundamental architecture of our planet, the layered structure of core, mantle, and crust, the global circulation patterns of atmosphere and ocean, the chemical cycles that regulate climate and habitability, all of this was established during those first 700 million years of Earth's history and continue to operate today. This continuity between past and present offers a unique perspective on our place in Earth's history. We are not late arrivals in the story of life, but in essence very closely related to the very structure of the planet itself.
Lava Earth, when the world was fire. Prologue. The memory of fire. The Earth you stand on today, the mountains, the seas, the forests, and the quiet cities that glitter under night skies, hides a memory so old it stretches beyond human history, beyond the rise of civilizations, beyond even life itself. Beneath the calm surface of soil and stone, the Earth remembers the time when it was not blue and green, but red and glowing. When there were no rivers, no clouds, no oceans. When the world was fire. This was not myth. This was not legend. This was the reality of our planet's birth. A violent, fiery beginning, when the Earth itself was molten and alive with flame. A time scientists call the Hadean Eon, a name taken from Hades, the underworld. What follows is the story of that age, the story of Lava Earth. Stardust and violence. Long before the Earth was born, there was a star, massive, bright, and ancient. Its life ended in fire, exploding as a supernova. That death scattered the elements, iron, carbon, oxygen, silicon, into the galaxy. Among this stardust was the material that would one day become Earth. Billions of years ago, a great nebula swirled in the darkness of the Milky Way. It was a cloud of dust and gas, turning slowly under the pull of gravity. From this cloud, the sun ignited, a newborn star surrounded by a disk of swirling matter. Within that disk, tiny grains clumped together, forming pebbles, then rocks, then mountain-sized bodies called planetesimals. They collided, merged, and shattered again until larger worlds began to take shape. One of these was the Earth. But it was not a calm world. It was born in collisions, each impact releasing heat so fierce it melted the rock itself. Earth's earliest surface was not solid. It was molten. It was lava. And then came the greatest collision of all. A Mars-sized body called Theia struck the young Earth. The crash melted much of the planet, blasting molten rock into orbit. That fiery debris coalesced into the Moon. The Earth was left scarred, glowing, unstable, a sphere of liquid fire. This was the true beginning of Lava Earth. Oceans of magma. Imagine looking at Earth then. There are no continents, no oceans of water. Instead, there is an ocean of fire, molten rock stretching as far as the eye can see, glowing orange and red like a living sea of flame. This stage is called the magma ocean. Temperatures soared above 2,000 degrees Celsius. The crust that tried to form cracked and sank again, swallowed by the churning mantle. Volcanoes roared endlessly, not as isolated mountains, but as vast fissures that split the ground. Rivers of lava spilled into lakes of fire, merging in endless cycles. Above, the sky was not blue but black, filled with thick clouds of steam and poisonous gases, carbon dioxide, methane, and sulfur. Lightning forked endlessly through the storm. The sun was a faint red disk behind the haze. This was not a world for life.
It was a furnace, sculpting itself in molten waves. And yet, in this chaos, Earth was laying its foundation. Deep inside, heavier metals like iron and nickel sank downward, forming the core, a blazing heart that still burns today, driving the magnetic field and shielding us from cosmic winds. Lighter rocks floated upward, creating the beginnings of a crust. But the crust was fragile. Again and again it shattered under new impacts from asteroids and comets. The Earth was trying to cool, but the universe was not finished with its violence. Fire from the sky. The skies above lava Earth were not peaceful. They rained fire. The early solar system was a battlefield filled with drifting asteroids and comets. Earth was struck again and again in what scientists call the late heavy bombardment. Some impacts were small, like fireworks in the sky. Others were cataclysmic, blasting craters thousands of kilometers wide, releasing energy greater than every nuclear weapon on Earth. Each collision reheated the surface, melting new seas of lava. The moon still carries the scars of this time, its craters frozen in silence. Earth, too, was scarred, though its surface would later heal. Yet these cosmic attacks were not only destructive, they carried gifts. Many of the asteroids and comets that struck Earth contained water locked as ice. With every impact, they delivered more of the oceans to be. Drop by drop, collision by collision, they seeded the future. It is a paradox. From destruction came creation. From fire came water. The sky of poison. Look upward. The air of lava Earth is not breathable. It is thick with steam, ash, and volcanic gases. Carbon dioxide dominates, trapping heat. Methane and ammonia swirl in toxic clouds. This atmosphere was heavy, suffocating, and fiery. It glowed with lightning, great storms flashing across the skies, striking the molten surface below. The lightning was not only destructive, it was also creative. It triggered chemical reactions in the gases of the air, producing complex molecules, the building blocks of life itself. But at this point, life was still millions of years away. For now, Earth was only fire and storms.
The first rain. And then, after millions of years, something changed. The Earth began to cool, slowly, painfully, but surely. Steam condensed in the skies. The thick clouds released their burden, and it rained. Not for a day, not for a week, not for a year, but for centuries. The rain hissed as it touched the hot ground, boiling instantly into steam. Drop by drop, it fell, battling against the fire below. Lava oceans hissed and cracked as the deluge continued. At last, water began to gather. Lakes formed, then seas, then vast oceans. The surface cooled enough for the first crust to harden. The Earth was still volcanic, still fiery beneath its skin, but above it, blue oceans began to spread. It was as though the world was breathing for the first time. Fire and water in balance. With oceans came new storms. With storms came winds and currents. Earth had transformed from a world of fire into a world of fire and water. Volcanoes still erupted, pouring lava into seas that boiled and hissed. Islands rose from magma, only to sink again. Ash clouds darkened skies, then cleared. The cycle of fire and water began, a cycle that continues to this day. Even now, every volcano you see is a memory of that time. Every eruption in Iceland or Hawaii is the Earth whispering its fiery origin. The meaning of fire. Humanity would not exist for billions of years, but when we did appear, We looked back on fire with awe. We worshipped it, we feared it, we used it. The Greeks told of Prometheus who stole fire from the gods to give to mankind. The Hindus honored Agni, the fire god, as a divine messenger. The Zoroastrians kept eternal flames burning in their temples. Why did every culture honor fire? Perhaps because deep in our unconscious, we remember. We remember that fire was the first force that shaped our world, that before there was life, before there was ocean or sky, there was fire. Fire is not only destruction, it is transformation. It is the boundary between chaos and creation. And in the beginning, Earth itself was fire. Chapter 8. Toward Life. With oceans now covering much of the Earth, chemistry awakened. Lightning struck the seas, volcanoes poured minerals into the waters, and sunlight filtered through toxic skies. Within this chaos, molecules formed. They gathered, combined, and danced in the waves. And somewhere, in a drop of ocean, life sparked. But that is another story. Epilogue. Fire eternal. Though the world cooled, the fire never left. It burns still beneath our feet, in the mantle, in the core, in the volcanic heart of the earth. Every eruption, every river of lava is a reminder of our origin. We are children of fire, shaped by flame, born from a world that once was nothing but lava. This is the memory of Earth. This is the story of Lava Earth, when the world was fire.